Okay, so continuing with our switching topics for today, first thing we're going to talk about here is gateway redundancy and high availability. Now, I talked about this a little bit before. What these two topics are going to be related to will be intra-chassis redundancy. So if we have a modular switch that has multiple route processors or multiple MSFCs or multiple RSFCs, if we have some legacy platforms, high availability a lot of times is going to be when maybe one of your power supplies goes down and the second power supply needs to take over, or the first forwarding engine, the route processor goes down, needs to fail over to the secondary. Okay, this is also called stateful switchover or non-stop forwarding. Now, gateway redundancy is going to be used for redundancy between chassis. So if we have switch 1 and switch 2 that are both forwarding traffic for VLAN 10 and VLAN 20, and they're also doing layer 3 routing for those VLANs, we want to come up with a design that if switch 1 goes down completely, so if the switch just crashes or it gets unplugged or there's some sort of cable failures, we want the other switch to be able to take over on its behalf. So this is going to both be intra-chassis redundancy, which would be the supervisor stateful switchover, and then inter-chassis redundancy, which is the first hop redundancy protocols like VRRP, HSRP, and GLBP. Now, in either case, when we're looking at the intra or inter-chassis redundancy, the goal of this is going to be service availability times. Now, especially if you are working for some sort of service provider, whether it's an application service like web hosting or email hosting, or whether it's a transit provider like you're selling transit bandwidth as an optical provider or Metro Ethernet, a lot of the times when you sell services to a customer, there's some sort of service level agreement or SLA that you guarantee that you are going to meet for them. Okay, the typical description of this is the 5 nines, that throughout the year you will guarantee 99.999% uptime, which basically means that you're going to have something less than like 5 minutes downtime throughout the year. So the key here is that we need to design the network with redundancy, both in terms of physical nodes, which would be like backup routers and backup switches, and then redundant links. So if one fiber link goes down, we want to be able to do an automatic repair to switch over to the other link from a layer 2 or a layer 3 routing point of view. Now, in most networks, you'll find that this is created in a layered implementation, meaning that there will have to be physical layer redundancy. Like in a SONET fiber network, we have very fast switchover times that can be just 5 to 10 milliseconds, that if a physical fiber cable goes down, SONET will be able to detect this and then switch over to the backup link. Now, that's going to be outside of our scope today because that's more layer 1 networking, so the actual optics of what's going on with the cabling behind the scenes. What we will be dealing with today is going to be layer 2 and layer 3 redundancy with things like spanning tree and our interior gateway routing protocols and the first hop redundancy protocols. So this would be more of the case of some sort of software failure, or maybe there is a full chassis that goes down or an individual link that is cut. We need to think about these type of situations during the planning phase of our network design, and we need to put some sort of target goal for what the convergence time is going to be of the network. So this means that, let's say we're building a campus network that's going to run IP telephony, so voice over IP over the Ethernet network, as opposed to the regular analog POTS network. Now, with this type of design, we need to look at the actual phone's application. So whether this is Cisco Call Manager or whatever other call managing software, we need to know what are the application's individual requirements. So if the network is down for more than 2 seconds, is the phone call going to drop? Or if the network is down then more than 10 seconds, do all the phones lose their registration? So the redundancy timeline is typically based on what the application requirements are going to be. If we're looking at just our typical office network that the users are doing web browsing and they're doing email, then it's probably not going to matter as much if their email is out for 10 seconds versus being out for 100 milliseconds. Now, what's actually interesting about this is that you would think one of the ways that you could add faster convergence and more reliability to the network would be to add more redundancy. So more redundancy in terms of additional links, additional nodes, then physical layer redundancy, like things like backup power supplies, backup batteries, that type of stuff. But when you get to the layer 2 and layer 3 redundancy point of view, a lot of the times when you make the network too complicated and you add excessive redundancy, it actually slows the convergence time down, and it takes more time for the network to heal based on a particular failure. Now, we talked about this a little bit yesterday in Rapid Spanning Tree Protocol, where one of the problems with RSTP is that if the network is very meshy, which means there's a lot of interconnects between the switches, or the network is very large, you can end up in some strange designs where it could take the network up to 2 minutes or more to reconverge, where you would expect something like Rapid Spanning Tree to have sub-second or maybe just a few seconds of convergence. So there's a lot of good design guides out there on Cisco's website and out from different vendor independent resources that talk about high availability. For the physical layer and the layer 2 stuff, a lot of that would be platform dependent. So the stateful switchover for the supervisors, you need to buy redundant modules for your 6500s or for your 7200s or 7600 routers. So that type of stuff is going to be more product related. But the design of the layer 2 and layer 3 protocols, there's a lot of good information out there, especially when it looks at case studies that says if this link goes down, these are the protocols that are involved. It's going to take X amount of milliseconds for HSRP to recover. It's going to take X amount of seconds for our IGP to recover. And what we can predict is, based on different failure scenarios, what is going to be the worst case recovery time in the network. And that's usually what you want to use as a good baseline to plan against what your target recovery time is. Now, one way that we can help to speed up the recovery time, so to lower the convergence, is to use the hierarchical design. So we talked about this before. Hierarchical design in switching means that you have an access layer that is logically separated from the distribution versus the core, meaning that if a failure happens in one switch block, it's not necessarily going to affect all the other modular switch blocks in the rest of the network. So we're doing what's known as fault isolation. So we're limiting what the fault domain would be for a particular technology. So if one link goes down and it's running layer 2 spanning tree, it doesn't necessarily affect all the other spanning trees in the rest of the network. Because by separating the layer 2 and layer 3 domains, this is what we are providing, is fault isolation. Now, there's a bunch of different technologies we can use to accomplish this redundancy, like the layer 1 stuff, like I mentioned, redundant power supplies. But from a technology point of view, design and implementation, there are going to be things like IGP in the core. So for layer 3 routing, we'll talk about this more when we get into the routing exam and how we can add high availability and low convergence to the layer 3 routing protocols. So doing things like sub-second hellos in OSPF, or doing things like the backup path design to make sure that we have feasible successors in EIGRP, so that we don't need to reconverge every time there's a topology change. And what we're going to focus on here today is going to be first hop redundancy in the access layer. So first hop redundancy is going to refer to redundancy for the default gateway of the end hosts on the network. So when we pick up our IP phone to make a phone call, the phone itself is not going to be running some sort of routing protocol. It's going to have a default gateway that's generally learned through DHCP. Now the problem is, when we make the phone call, we're trying to get to our call manager server or send our UDP voice packets out. If that default gateway is down, then it doesn't matter if the rest of the network is up. End-to-end connectivity is not going to be there. So this is the first thing that we're going to be targeting today. What happens if that first hop access switch goes down, what are the different ways we can add redundancy in the access layer? Now, most of these will be related to layer 3 protocols today. So HSRP, VRRP, GLBP, those would be considered layer 3 protocols. But we do need to consider their interaction with the layer 2 that is underneath. So what this means is that if we have switch 1 as the active HSRP router, we would also want to make sure that it is the spanning tree route for whatever VLANs that it is servicing. Because we may be looking at not only our layer 3 convergence for HSRP, but also some layer 2 convergence time that has to do with spanning tree. So when we look at this on the command line and actually do our testing, it'll make a little bit more sense why we need to synchronize both of these together. Okay, so as I mentioned, the end hosts, they typically don't route packets per se into the network. They're just going to blindly send all of the traffic to their default gateway that is for a destination not on their own local subnet. Now, we talked about this a little bit before in design, what used to be called the 80-20 rule, where 80% of the traffic was local and 20% of the traffic is remote. In today's networks, a lot of times that paradigm is flipped. So it's going to be the 20-80 rule, where 20% of the traffic is local, 80% of the time it's going through the gateway to some remote destination. Okay, there's a question here. What is FHRP? That's the first hop redundancy protocol. So we'll talk about what they are in a second here, but it's just a generic term that refers to this layer 3 gateway redundancy. So gateway redundancy and first hop redundancy, same thing here. So what we're trying to do with this type of technology is to make sure that the operation is transparent to the end host. So when you pick up the phone to make your call, you don't know whether you are actually being serviced by switch 1 or switch 2 or switch 3 as members of the redundancy group. So as long as the phone call gets through, that's all the end user cares about. They don't want to know what's going on behind the scenes in the rest of the network. Now, at the same time, we don't have to add complexity to protocols like DHCP or do some sort of hack on routing at the end host. We're just going to deliver them one default gateway address through DHCP. Then the network itself will do some redundancy based on that particular value that they are assigned. Now, what we'll see here in the case of any of these protocols we will look at, which are going to be HSRP, VRRP, and GLBP, the thing that is in common with all three of them is that IP's address resolution protocol is going to tie everything together. Now, we talked about ARP before when we were looking at layer 2 switching within our own VLAN versus layer 3 routing. And address resolution protocol is used to map the layer 2 MAC address to a layer 3 IP address. So when we're sending traffic to a destination over Ethernet, we need to know what is the next hop layer 2 MAC address, and then what is the final destination IP address. Now, if we have a case where we have two hosts in the network, we have A and B, they want to send packets to each other using IP. From host A's perspective, it will look at the destination of host B, and it's going to do some basic binary logic with its own IP address and its own subnet mask. It's going to try to figure out, is host B on the same subnet as I am? Now, if A finds that B is on the same subnet, it says B should be in my broadcast domain, so I can send them directly a layer 2 broadcast, which is going to be going to all Fs, to ask them what is their MAC address. So this means that host A is going to ARP directly for host B. Now, if it already has the entry in the ARP cache, then it's going to skip over that. It means that previously it had already ARPed for B. But the vast majority of the time, B is not going to be in the local subnet. So if B is not in the same subnet as A is now going to look at to see what is its own default gateway. Now, we will still be sending the layer 3 packet to host B. So the layer 3 IP address is going to be the final destination, but the layer 2 address will be the intermediary next hop. So it's going to be whatever router or layer 3 switch is on the same VLAN as host A. So in that case, we'll do either two things. We'll consult the ARP cache to see if we already know the gateway's MAC address, or if we don't know the gateway's MAC address, then we're going to send an address resolution protocol request for them. Now, this second step here, when we are ARPing for the gateway, this is where the first hop redundancy protocols are going to come in. Essentially, what we're going to do is virtualize the MAC address of the gateway so the end host doesn't actually know what physical device we're sending the traffic to. So address resolution protocol, this is what is going to allow us to have the redundancy. So here we have a basic topology where we could demark the access layer versus the distribution layer, saying that switch 1 and switch 2, these are our access switches going down to the end hosts, where switch 3 and switch 4, this is our distribution layer, and this is where our layer 3 routing is occurring. Now let's assume that host A and host B are in different VLANs. This means for them to communicate, they're going to have to go to an intermediary layer 3 device. They need to do layer 3 routing to reach each other. So again, host A finds that B is in a different subnet. It now needs to ARP for its default gateway. Now let's assume in this case that A is in VLAN 10, B is in VLAN 20, and switch 3 is the default gateway for both VLANs 10 and 20. So we have some layer 3 interfaces, interface VLAN 10, interface VLAN 20. So based on however the layer 2 CAM table works, host A is most likely going to route, or I should say switch up to switch 1, and then probably directly connected to switch 3. B's path is probably going to look something like this. Okay, this would depend on what the layer 2 spanning tree path selection is. So if switch 3 were the root bridge both for VLANs 10 and 20, then switch 1 and switch 2, they're most likely going to take that directly connected path. So in any case, the layer 2 traffic is going to get up to the switch somehow. Now once it gets there, switch 3 is going to do that layer 2 packet rewrite. So it's removing the old Ethernet header, putting a new header on, and then forwarding it into the destination VLAN. So from A, it's going to go up to switch 1 to switch 3. Switch 3 moves the traffic into VLAN 20, then down to switch 2, then down to the final destination. Now the problem that we could run into here is that if switch 3 goes down, even though there are multiple backup physical paths between the devices, so we could just reroute around this way, go up to switch 4, and then down. If switch 4 is not routing for that VLAN, it will not be able to move the frames between VLAN 10 and 20. Because to move between broadcast domains, we need to do that layer 2 packet rewrite. So this is what we're trying to avoid by using the first hop redundancy protocols. We want to figure out some sort of design that we could send the packets up to switch 3. But if switch 3 goes down, we want to be able to reroute the packets to another layer 3 device on the segment. So switch 3 and switch 4, they're going to have some sort of protocol, some sort of communication mechanism to figure out who is actually going to be forwarding the traffic for VLANs 10 and 20, and who is doing the layer 2 packet rewrite for that VLAN. So basically, who is doing the routing. Now, regardless of the protocol that we use to accomplish this, and we'll see shortly there's 3 different variants that we could use, the logic is always going to be the same. First off, we will have layer 3 devices, so layer 3 switches or layer 3 routers, that are running together in a redundancy group. So in the case of the previous diagram, it would be switch 3 and switch 4 who are in this redundancy group. Now in the group, we are going to have a virtual IP address that will be used as the default gateway for the hosts. So switch 3 is going to have some real IP address. Let's say it's 10.0.0.3. And switch 4 is going to have some real IP address, let's say 10.0.0.4. So that would be for normal IP connectivity between them. They're unique addresses. But at the same time, they will be sharing a virtual address, let's say 10.0.0.254, that will be assigned as the default gateway to the end hosts. Now, since both of the neighbors are sharing the same IP address, we know that we can't have both of them forwarding at the same time. We can't have duplicate addresses on the link, because otherwise we would corrupt the ARP cache and we would corrupt the CAM table. So basic logic of IP routing, you have to have unique addresses in order to send traffic to each other. So we need some sort of mechanism to figure out who's actually using the virtual address. And it's going to be this binding of the virtual IP address to the layer 2 MAC address that is virtualized. So whichever device is considered the active physical router, so whoever wants to do the forwarding, when an ARP request goes to the virtual IP address, they will respond with their own MAC address. Now, whether this actually is their own MAC address or whether it's some address they're making up, doesn't really matter. The different protocols implement it a little bit differently, but the basic logic is that the active router replies to the ARP request. Now, if the active router goes down, the one that is in the backup state is going to take over for that virtual IP address and take over for that MAC address. So there's going to be some sort of keep alive mechanism between the neighbors in the group, and we'll use this to detect if one of the neighbors is having problems. So we could say send a hello message every 2 seconds, and if I miss 3 of them in a row, so after 6 seconds, the backup router is going to come on and take over the active status. But the idea is that from the end host's perspective, they don't need to update any information in their ARP cache, because we're virtualizing the association between the gateway IP address and the underlying MAC address. Now, specifically implementation-wise, there's 3 different protocols we can use to accomplish this. They're all going to have that same major functionality, which is we're virtualizing the IP address of the gateway versus the underlying MAC address. We're checking to make sure that the active router is functional. So there's going to be some sort of keep alive between the neighbors. And if the active router goes down, the next router in line is going to step up. So someone is going to take over forwarding for the virtual IP address in the case that there's a failure. So this is the same major functionality for all 3 of them. The difference is that there will be some minor enhancements, like gateway load balancing supports load balancing, as you would guess, versus HSRP and VRRP, which do not. Now, also, since there are 3 different protocols, you probably assume there's a different specification behind the scenes. So they use different transports, different multicast addresses, different IP protocol numbers, different UDP ports, that type of stuff. But the same functionality, major functionality, is going to be the same for all 3 of them. Now, HSRP was the first iteration of these first hop redundancy protocols, because it was Cisco proprietary. So this has been around for quite a while. Now, being Cisco proprietary, as you can imagine, it means that there's no interoperability. So this would only work between 2 Cisco routers or between 2 Cisco switches, or maybe like a router and a switch. Now, HSRP uses UDP multicasts going to the address 224.0.0.2, which is the all routers multicast address. So it means all multicast-enabled routers on the link will be listening for the communication. 95. Now, HSRP uses the logic of an active and a standby router. The active router will be listening for any ARP requests that go to the virtual IP address. When the ARP request comes in, the active router responds with its own virtual MAC address. So it now means that the actual traffic from the host, as it forwards to the default gateway, it goes to the active router. The standby router is simply listening to make sure that the active router is up by doing a basic keep alive mechanism between the 2. And if the active router goes down, meaning it doesn't receive those keep alives within whatever configured time frame we have, standby router is going to promote itself to the active status, and it takes over for the virtual MAC address. Configuration-wise, this is going to be the standby command at the interface level. The next iteration here, the Virtual Router Redundancy Protocol, is an open standard. It's defined by RFC 3768. This is basically the open standard response to HSRP. So the advantage here is that there is interoperability. If you have a Cisco switch and you have a Foundry switch, potentially they could run VRRP together. So same type of logic where we have active and standby for HSRP. This is going to be replaced by master and backup in VRRP. So transport behind the scenes is a little bit different. We're still using multicast, but we're using a new address, so 224.0018, and it uses its own IP protocol number, which is 112. So this means it has its own transport. It doesn't use UDP, it doesn't use TCP, it uses its own protocol. So similar to how OSPF or EIGRP use their own transport protocols. Now the same logic for master backup as we had for active and standby. The master router is the one that will respond to ARP requests with its virtual MAC address. The master router is the one that's actually forwarding the traffic. The backup router is going to be running a keep alive with the master router. If the master router does not respond, backup router promotes itself to the master status and it takes over for the virtual MAC address. Configuration-wise, they're going to be very, very similar. You could essentially take an HSRP config, change the standby command to the VRRP command, and the implementation is going to be almost identical. So behind the scenes it'll be different, but from the host's point of view, they're not going to know whether you're running HSRP or VRRP. The third one we have Gateway Load Balancing Protocol, or GLBP. This is also Cisco proprietary. Uses a different UDP multicast address, it's 224.00.102, and it uses port 3222. Now the main advantage of the third one, GLBP, over HSRP and VRRP is that there are multiple active routers at the same time. So it's going to provide load balancing for us. Now what's neat about this protocol is that there's still only one virtual IP address. So the hosts on the segment, they get one single default gateway. But GLBP decouples the logic of replying to the ARP requests from the actual forwarding of traffic. And we're separating it into two separate roles. We call them the Active Virtual Gateway, the AVG, and the Active Virtual Forwarder, the AVF. Now, when a client sends an ARP request to the gateway, the Active Virtual Gateway responds with one of the forwarder's MAC addresses. So if we have three virtual forwarders with MAC addresses A, B, and C, when the Active Virtual Gateway receives an ARP request for the virtual IP address, they will respond back to the host with one of the MAC addresses A, B, or C. So they're responding on behalf of the virtual forwarder. This means that when the actual traffic flow occurs, the host is sending the traffic towards the same virtual IP address, but based on the layer 2 MAC address, it's going to go to a separate active virtual forwarder. Now, the active virtual forwarders will back each other up, meaning they run the same type of keep alive logic as HSRP and VRRP do. If one of them goes down, one of the virtual forwarders can take over multiple virtual MAC addresses at the same time. But what you would see with this protocol is that in the ARP cache of the hosts on the segment, they will not all agree on what the MAC address of the default gateway is. So different hosts will have different MAC addresses corresponding to the same IP. And it's going to allow us to do load balancing. So we can get pretty complex with the logic of how the load balancing works. We can do a weighting system that says for every 3 ARP replies that go to router 1, we want 1 ARP reply to go to router 2. So if router 1 is a faster router, or maybe it has better connectivity, to the rest of the topology, we can configure some sort of complex weighting process. There's a question, so the load balancing is always changing based on the last ARP, correct? Now, what you'll see with the ARP cache is kind of interesting. On a lot of the hosts, the ARP cache timer is multiple hours. So once your end PC or your whatever box, could be your IP phone, once they ARP for the default gateway, a lot of the times they're never going to change that assignment. So as long as they keep using the gateway for some destination, the ARP entry is going to keep refreshing. So you don't get a true load balancing like on a packet by packet basis, but you can end up in at least some better distribution than having just one forwarder and then a bunch of backup routers. Because the problem is, let's say that these are 6,500 switches in your distribution. Basically means that you have one switch sitting there working all the time, and then another switch sitting there that's doing nothing. That would be the case with HSRP or VRRP. With GLBP, at least you can try to get some distribution between the two of them, so one of them is just not sitting there waiting to take over the active role. Now, beyond this basic feature for all three of them, where we are virtualizing the IP address association to the ARP cache, to the MAC address request and reply, they generally support the same features. Beyond this, things like doing authentication for security. You could run multiple groups per interface if you want to try to do some sort of load balancing within the VLAN. So we could say that half of the routers are going to default to the gateway address .1, or not routers, half of the hosts. So half of the hosts in the VLAN default to the gateway address .1, half of them default to the gateway address .2. Where .1 and .2, both of them would be redundancy groups on different routers that are backing each other up. So there is kind of a hack you can do with load balancing for HSRP and VRRP. We'll see that when we get to the command line. That would be by using the multiple groups per interface. Now, the third one here is very important. It's a feature known as preemption. This is used to allow the backup router or the standby router or the active virtual forwarder, in the case of GLBP. So basically the backup device to immediately take over the active device status based on some sort of criteria that we define. Now, the default criteria would always be that if the active router is completely down. So if switch 1 is the current gateway and switch 1 reboots, then switch 2 should always take over. That's going to be the same functionality between all three of the protocols. But by configuring this preemption feature, we can define different criteria of the operation of the network that could say, for example, if my T1 link to the ISP goes down, I want someone else to take the active status away from me. Or if one of my links inside an Ether channel bundle goes down, I want someone else to take over the active status. So we'll see once we get to the command line how actually this occurs. There's going to be an election process that the three protocols run through, simply based on a priority. Basically means whoever has the highest priority is going to be the active forwarder. It would be the active router in HSRP, the master router in VRRP, or an active virtual forwarder in GLBP. So with preemption, we can play around with this priority value, try to decide based on the network conditions who's actually going to be forwarding. Now, in newer versions, these protocols can also integrate with a feature that is known as enhanced object tracking that goes along with a feature that is known as the IP Service Level Agreement, or the IPSLA. Now, this is a really neat feature in iOS. We'll spend a couple minutes playing around with it today on the command line. But it adds application level awareness to the network in order for the routers or switches to respond based on different conditions that are happening in the network. So let's say, for example, that we have a basic network design where we have two separate links to two different service providers. So we have two internet connections. One of them is from AT&T, one of them is through British Telecom. The AT&T link is much faster than the British Telecom link. Let's say that we bought an OC48 versus just a T3 connection from one of them. So what we want to do with our design is try to send traffic out the faster link. We're going to send traffic out the OC48 if we can. Based on the enhanced object tracking feature, we could configure the network to say, I want you to ping some address out on the internet. I want you to ping this address every 3 seconds. If you don't get a response, or you get a response that exceeds 100 millisecond latency or 500 millisecond latency, we can change the priority of the underlying first hop redundancy group in order to try to forward out the different link. Okay, so pinging would just be one example. There's a lot of other application level awarenesses that you can add in. For example, for IP telephony, if your service provider guarantees you that you will get no more than, let's say, 60 millisecond latency, we could set up an IPSLA instance that says use UDP packets to check what the delay of the circuit is. If the delay of the circuit goes beyond 60 milliseconds, take that router out of its active state for HSRP and send it over to a different router who has different connectivity to the network. So we'll see. We'll look at the documentation for this too. There's a lot of real detail that you can get into as to how the SLA tracking works. Most of it is going to be outside of our scope, but it is good to know that it is there. There's a lot of really neat application aware things that you can do now in iOS. There's a question: is that like the layer 4 through layer 7 health keep alive and use this to switch to another virtual router? Exactly. Okay, so let me drop another example of it. So let's say, for example, we have 2 different DNS servers in our network, or web servers, whatever application that we're trying to run. Okay, so we're running some sort of application on these 2 servers. Let's assume that they are mirrors of each other. They're web mirrors or they're DNS mirrors. Okay, then in front of these, we have some sort of redundancy group. We'll say that we have router. We'll have router 1 and router 2. And now this doesn't necessarily have to relate just to first hop redundancy. The enhanced object tracking and the IPSLA, it has a lot of other integration into different features in the iOS. This is just one of the examples that we could use for it. But what we can do here is let's say on this router 1, that if packets route to router 1, they end up using server number 1 as the mirror. If they route to router 2, they end up using server number 2 as the mirror. So depending on which particular router is forwarding for the group, that's going to determine which application server that we get to. So we're trying to do some sort of application level redundancy. Now what we could potentially do with an IPSLA instance is to tell the router to send an HTTP GET to the web server to try to get some page, let's say index.htm. Or we could say, have it send a DNS query for a particular web address or a particular domain name, fully qualified domain name, and see if we get a response back in. Or we could say something as simple as just send them a ping. But what would be the difference from an availability point of view? What would be the difference between just pinging the server versus sending them an HTTP GET or sending them a DNS query? Could there ever be a case where the server would respond to a ping, but maybe the Apache service was down, or the DNS daemon was down? So by adding the application level awareness, we can say that really the ultimate goal here is not just that I can ping the server. I want to make sure that it's actually serving its application. So if I send the HTTP GET to them and they do not send me the web page back down, that means there's probably something wrong with the server. What I can then do is tell router 2, I want you to take over as the active status. So then from the rest of the network's perspective, it's transparent because these two routers, they're sharing some sort of virtual IP address that the rest of the network doesn't have to worry about. Okay, there's a question, checking application reachability. Does it also support TCP slicing for DDoS attack prevention? There's some other tools in there we'll talk about a little bit later in security that you would use to prevent denial of service attacks. But let's say someone is doing just like a basic TCP SYN attack. So whether they're doing that against the web service or whatever other TCP service, maybe it's a mail server. If the router sends through the SLA instance the HTTP GET and the server doesn't respond, we don't really care if it didn't respond because Apache is down or because Apache is under denial of service. From the end user's perspective, it's going to be the same result. The result is that the web service is not working. So then based on that, we could tell the routers to take some sort of action and basically change the conditions of the network and change how the underlying routing infrastructure works. So it's a really, really powerful feature. There's a lot of cool application level awarenesses that are now available in the IPSLA feature, and then how they tie to different other features in iOS. Okay, we'll talk about it later in routing when we also get to the policy routing feature, and we'll talk about it a little bit in static routing as well. Okay, so the idea about this object tracking feature and the IPSLA is that we want to select the gateway based on just more than whether the gateway is up or down. We want to do it based on some sort of network condition. Now, it could be as simple as tracking an interface. So if my DSL link to the internet service provider goes down, I want to take myself out of the active status. Or it could be one of those complicated IPSLA operations. Now, GLBP, in addition to this, you can also use it to change the weighting, which affects the load balancing algorithm between the active virtual forwarders. With HSRP and VRRP, it's pretty cut and dry because there's only one person who can forward at a time. But with GLBP, it can get much more complicated, where you say maybe I have 3 gigabit links in an ether channel together. So I have a single pipe that is equivalent of 3 gigabits per second. If one of the links goes down and the ether channel falls back to 2 gigabits per second, then maybe I'll reduce my weighting from 3 to 2 so I can offload some of the network traffic onto one of the other virtual forwarders. So the syntax will be pretty straightforward. We'll look at this on the command line for the tracking. And then for the IPSLA instance as well.